You look up at the night sky, and it's easy to think of it as this vast empty space. But what if I told you that right here in our cosmic neighborhood, there's a ton of activity you can't even see?
That's absolutely right. And in this deep dive, we're looking at a brand new study that's done just that. Scientists used the Meerkat radio telescope, pointed it at a twinkling pulsar,
And found what?
found this whole network of unexpected plasma structures swirling around near us. It's pretty fascinating stuff.
Okay, yeah. The source we're diving into today is an article from NDTV, and it's covering this research published in Nature Astronomy. So our mission really is to unpack what these plasma structures are, how on earth they found them, and I guess why it matters, why it's making us rethink the space right around Earth. Because, you might think space is empty, but this research, it really shows that's far from the case.
Definitely. So maybe let's start with the main character here, this
Right.
twinkling pulsar. What exactly is a pulsar, and why does it seem to twinkle?
Okay, right, good place to start. So the study looked at one called J04374715. It's about 512 light years away, which is, relatively close in cosmic terms.
In our backyard, sort of.
Yeah. And a pulsar is, well, it's what's left after a big star explodes. A supernova. You get this incredibly dense neutron star left behind.
Super dense, spinning incredibly fast.
Exactly. Spinning like crazy and shooting out these beams of radio waves.
Yeah.
Like a cosmic lighthouse beam sweeping past us. And this particular pulsar also has a powerful wind, just particles streaming off it.
Okay, and this pulsar, it's not just sitting there, right? It's moving.
Right, it's moving and fast. Supersonically through what's called the interstellar medium.
Which is just the stuff between stars,
Yeah.
gas, dust, plasma.
Yeah, all that thin stuff out there.
Yeah.
And because it's moving so fast with this wind, it creates a bow shock out in front.
Like the wave off the front of a speedboat.
Perfect analogy. A shock wave of heated gas piled up ahead of it. Sometimes you can even see light from these things.
Okay, so that's the bow shock. But the twinkling, or scintillation, as scientists call it, that's different.
Yeah, that's different. That happens because the radio waves from the pulsar have to travel through all that interstellar plasma on their way here. And that plasma isn't perfectly smooth, it's turbulent.
Ah, okay, so it's like looking at lights through heat haze, or stars twinkling because of Earth's atmosphere.
Exactly like that. The uneven plasma sort of bends and scatters the radio waves randomly. So from our perspective, the signal strength goes up and down, it twinkles.
Right. And the amazing part is that this twinkling, which sounds like noise, actually contains information
Information about what?
about the plasma itself. The way the light twinkles, the patterns in it, tells us about those otherwise invisible clumps and structures in the plasma that it passed through. It's like using the distortion to map the thing causing the distortion.
Huh. So the problem, the twinkling, is actually the key.
Precisely. It's a powerful probe of the interstellar medium we wouldn't have otherwise.
Okay, this is where it gets really interesting then. The researchers weren't just looking at the general twinkling. They found something specific called scintillation arcs. What are those?
Right, so imagine the twinkling isn't just random flickering. Sometimes, within the interference pattern, how the scattered waves add up, you see these ordered shapes, arcs.
Ordered shapes.
Yeah. Think of it like if light shines through layers of differently curved glass, you get specific patterns. These arcs are like that. They're created when the radio waves pass through distinct compact clumps or layers of plasma.
And these arcs tell you what?
They tell you where those clumps are, essentially, between us and the pulsar, and even how fast they might be moving across our line of sight. The shape and curvature of the arc is like a fingerprint for that specific plasma structure.
So it's like doing a CT scan, but using radio waves and plasma.
That's a great way to put it. Yeah, a CT scan of the interstellar medium using the pulsar as the source. Each arc gives you a piece of information about a specific plasma structure.
And what was so special about the arcs they found in this study?
Well, usually you might find maybe one or two clear arcs for a pulsar. It tells you about the most dominant structures. But here, they found 25.
25 for just one pulsar.
25 distinct scintillation arcs. It's the most ever seen for any single pulsar, by far.
Wow, okay, that's a lot. What made that possible? Why so many here?
Two key things, really. First, this pulsar, J04374715. It's the closest millisecond pulsar. Millisecond just means it spins incredibly fast, hundreds of times a second.
So it's nearby, Relatively speaking, 512 light years.
Exactly, relatively close. And second, the telescope they use, Meerkat in South Africa, it's exceptionally sensitive. It can pick up these really subtle details in the twinkling pattern that older telescopes would just miss.
Got it. Proximity plus sensitivity equals a whole lot of arcs.
Precisely, a much clearer picture than we've ever had before.
Okay, so they found 25 arcs. Where were the structures these arcs pointed to? The article mentioned something called a local bubble.
Yeah, this is maybe the biggest surprise. So 21 out of those 25 arcs, they correspond to plasma structures located within the local bubble.
Right, the local bubble. Remind us what that is.
So the local bubble is this region of space our solar system is currently moving through. It's thought to be this large cavity, maybe up to 1,000 light years across.
A cavity. How did it form?
The idea is that a series of supernovae, maybe 14 million years ago or so, exploded relatively nearby and basically blew out a lot of the gas and dust, creating this bubble of very hot, very low density gas.
Hot, like millions of degrees Celsius hot.
Yeah.
And mostly empty.
That was the picture, yeah. Extremely hot, very tenuous gas filling this void, mostly empty compared to the average density of the galaxy.
Okay, so finding 21 distinct plasma structures inside this supposedly near-empty, super hot bubble.
Exactly, that's the shocker. It means the local bubble is, well, not nearly as empty or simple as we thought. It seems to be filled with these compact plasma structures.
And does that change the temperature picture too, if these structures are there?
It strongly suggests it does. For these kinds of structures to exist and cause the scintillation they observed, the plasma can't be millions of degrees everywhere. In these regions, at least, it must have cooled down significantly.
Cooled down to what?
The study suggests maybe around 10,000 degrees Celsius. Still hot by Earth standards, obviously, but vastly cooler than the millions previously assumed for the bulk of the bubble.
Wow. So our local neighborhood isn't just hot and empty. It's got these cooler, denser patches scattered throughout.
It looks that way. It implies a much more complex thermal history and structure for the local bubble than the standard model suggested. It's a pretty major revision of our local map.
Okay, that's fascinating about the local bubble. But there were 4 other arcs, right? The article said they let scientists look inside the pulsar's bow shock.
Yes, and this is arguably just as groundbreaking, maybe even more so in some ways. We've talked about the bow shock earlier, that wave ahead of the pulsar.
Right, the speedboat wave.
Yeah. We think these are common around pulsars, but they're really faint and hard to observe directly. Only a handful have ever been studied in detail.
And scintillation let them see inside this one.
For the very first time, yes. Those remaining 4 arcs originated from plasma within the bow shock structure itself. It gave them that CT-like view again, but this time slicing through the layers of the shock.
So what did the CT scan of the bow shock show?
Well, first, they could build a 3D model. It looks a bit tilted, which probably tells us something about the pulsar's exact motion or the magnetic fields around it. But the really weird thing...
There's always a weird thing, isn't there?
Hey, seems like it. One of the plasma structures they mapped inside the shock. It was moving towards the front of the shock.
Wait, towards it. But isn't all the material supposed to be flowing away from the pulsar, pushed outwards by the shock?
That's the standard picture, yes. You expect the flow to be generally outwards, away from the pulsar after it hits the shock front, finding a structure moving inwards back towards the shock front. That's highly unexpected.
Does that ever happen in simulations?
The article mentions that such backflows are sometimes seen in very complex computer simulations, but they're considered pretty rare and depend on specific conditions. Seeing it observationally like this, it's a big puzzle.
So this finding could really challenge the models of how these bow shocks actually work.
Absolutely. It suggests there are dynamics happening within these shocks that maybe our current theories don't fully capture. It's going to drive a lot of new modeling work trying to figure out how you get plasma moving against the main flow like that.
Incredible. So they didn't just find unexpected stuff around the pulsar in the local bubble, but also unexpected behavior within its own shockwave.
Exactly. It really demonstrates the power of this pulsar scintillation technique. It's opening up ways to study plasma physics in environments we just couldn't access before. Studying invisible structures and mapping flows inside faint shockwaves, it's pretty remarkable.
And the article suggests this is just the beginning, with better telescopes.
Yeah, with newer, even more sensitive radio telescopes coming online, like the Square Kilometer Array eventually, we can expect to use this technique on more pulsars, fainter pulsars, and get even more detailed maps. There's likely a lot more hidden structure out there waiting to be revealed.
Okay, so let's try and wrap this up for everyone listening. What's the big takeaway here?
I think the main point is that this twinkling little star, this nearby pulsar, has acted like a flashlight, revealing unexpected complexity right in our cosmic neighborhood.
Right. It showed us the local bubble isn't this simple, empty, super hot void. It's got these cooler, denser plasma structures floating around in it.
Which changes our picture of our local galactic environment.
Yeah.
And then give us this unprecedented peek inside a pulsar's bow shock.
Yeah, finding plasma moving in ways that, frankly, challenge our current understanding of how these things are supposed to work.
Exactly. It shows that what might look like empty space, or even phenomena we thought we understood, can hold surprising secrets.
So to sum up this deep dive, we use this twinkling pulsar, J04374715, as a probe. It revealed dozens of hidden plasma structures, most surprisingly within our own local bubble, suggesting it's cooler and more complex than we thought.
And it also gave us the first CT scan inside a pulsar bow shock, finding plasma moving in unexpected ways that will likely force scientists to refine their models.
It really makes you wonder, doesn't it? If just looking closely at one nearby twinkling object can reveal all this unseen structure.
Yeah, how many other parts of the universe that we currently label as empty or simple are actually filled with complex phenomena we just don't have the tools to see yet?
What other big assumptions are we making about the cosmos that future observations might just completely overturn? It's kind of mind-boggling.
It definitely keeps things interesting. There's always more to discover.
Absolutely. Well, if this deep dive into twinkling pulsars, the local bubble, and plasma physics got you thinking, definitely dig deeper into those topics. There's a whole universe of amazing science out there.